Good evening, everyone. This is Obi-Wan Pez for N-Simplex Pachinko. Tonight, I'm going to talk a little bit about the four-color theorem in um, graph theory, and a little bit about the history of it, and my experience with it, although it's very small, very, very tiny amount. And then we'll get into either user questions or talk about any number of other things I got laying around here. So, the four-color theorem comes from a larger problem that existed earlier, or a less generalized problem called the five-color theorem, which said that all you need are five colors in order to color any specific map or a specific plane, planar figure. So what you could do is make any sort of map, like, a bunch of countries might exist somewhere. This is going off the edge of my screen, but whatever, it's cool. And in order to color this particular map, what we would do is just start anywhere and pick a color. So this will be color number one, it's just going to be black. And then this entire region is going to be colored in with black. That's number one. Okay, a country that is touching it cannot also be black, so we're going to call the next one over here color number two, and that's going to be red for us tonight. Color everything within its borders red. All right, one that is touching both of them cannot be red nor can it be black, and so this must be color 3. We'll call it blue. And then as we come around, some people might think, oh, well, this is going to be a fourth color. But here's the thing. This country right here is actually not bordering a red country, and so this one here can be colored red. So we kind of basically go back to like prioritization. So what is the earliest color that we are allowed to use because they're not actually touching this particular kind of country? So this one can be color 2 again, which also means that the next one over here can be color 3, which is going to be blue again. Because again, it just can't be black and can't be red. And then this one over here is touching numbers 2 and 3, but not number 1, so therefore it can be colored in with number 1. So back in the 1800s, a mathematician by the name of Alfred Kempe came up with the idea that no matter how complex your map is, you only must use 5 total colors. And he was able to prove it by using a proof by contradiction. Now, one of the things that you can do in graph theory are to construct a map using what's called a graph. And in graph theory, this is like, number 1 will be shown as a node. And then every country that it borders will also then be connected to that node. So we have 1, 2, 3, 4 countries which are around it, roughly in these positions. And again, they are connected to this one here. So again, country 1 on our left side was here, and roughly in this order we have our other 4 countries. These were in order. A country 2 here, which was connected to a country 3 over here. connected to a country 2 over here, connected to a country 3, oops, a country 3 over here, and both country 2 and 3 at the bottom here are connected to a different country 1 down here, or a country having color number 1. And essentially what we look at is just that no two nodes can possibly connect a country 1 to a country 1, or country color 1 to another country color 1. So if, for instance, this country were to extend its influence around country number 3 and touch country number 1 here along this border, then this could no longer be black. We could no longer use black to color this particular country. We would need to take out this particular color. And say, oh, well, we can't do that anymore. So let's redraw the borders. We would need to redraw the graph. This can no longer be color 1 because now this country connects with this country here. So what do we have to do? Well, we're going to have to use a 4th color because it's already connected to 2 and 3, and now it's connected to 1. It can be none of those colors, therefore it must be color number 4. So, green. Apologies to anybody who is colorblind. This is going to be torture. So, this is going to have country color 4 going through here. At this point, what happens is we say, okay, now how else can we connect a whole bunch of dots that are in here, which will force us to use a 5th color. So the 4-color theorem uses graph theory and says, well, you can't actually do that. If you notice that if we were to build an extra node, let's say another country is formed in this space here, then what color would it need to be? Well, if it is connected to the maximum number of countries that it can, that's going to be 1 and 3 and 4 through here. Which means that the only number it can't connect to, and therefore the color it must be, is 2. If we try to build out any other particular kind of node, like this one here, okay, well that's going to connect to 3 and 2 and 4 and 1 this way. Then actually this will preclude something else. So if we were to essentially build out a country that touches now 4 and 2 and 3 and 1 going all the way around the edge like this, this is going to be an interesting problem because now it seems like we have to use a 5th color in order to make this work. However, what's going to happen instead is that we can notice that color number 4 here, which one is it? Yeah. Either of the countries labeled 2 or 3 up top here don't have to be 2 or 3. It could be that we could cut out the 3 from this position and say that this country here is no longer, or is not, touching number 4 over here. And so now this country will also be a green country here. And therefore this big one going up top is no longer going to be a fifth color. This is now acceptable to be blue. And pretty much every counterexample that you will ever see for the four-color mapping theorem will be of this type of error, wherein one of the other colors that's being used doesn't have to be used anymore when you start introducing new countries in. So simply by swapping this 3 that was here, we can now move it out, make it the same as another country that it's not touching. And now suddenly, oh, look at that, it works. Works just fine. And if we try to make 4 over here touch this 4 over here, then again, these two can't be the same color, but that means that this 2 will then be isolated from this 3, and they can both be blue. So this will shift from a 2 to a 3, which will allow this 4 to change to a different color, and it cascades out from there. Or potentially this 4 here will change to something completely different as well. So any counterexample that you come up with, just trust me on this. You're going to find out that you're basically cutting yourself off in here. In that you can just renumber. This one can now no longer be connected to 4 because it has been locked out from being able to connect with this 4 over here. So now this one's going to be a 4. Now this one over here is going to be a 3. And if you think, oh, well, I'm going to connect this 3 down to the other one. Oh, look at that. You can't do it. The important part of this graph is that it is non-intersecting. So you're not able to have lines that go over each other because that's not how countries work on a map. Now, granted, you could actually have a discontinuous country in real life. So you could have a country that has 2 separate pieces of land. And there are some cases, I mean the United States for example, right? We've got the contiguous 48 states and we've got Alaska. Alaska is connected through Canada to the contiguous 48, and therefore we want to keep them to be the same color. So if Alaska had a lot more connections, it could potentially be an example that does break the 4-color theorem for like real life. But in terms of mathematical stuff, you'd be able to change the color of Alaska to be something that is not the same as the contiguous 48 and still have it be mathematically sound. Again, it doesn't make any sense in terms of real life because you want Alaska to be the same color as the contiguous 48. All right, same thing happens throughout the rest of the world. If there is ever any discontinuous or discontiguous set of land that belongs to one country, then you might have a problem with the 4-color theorem working for that particular map. However, again, this still works mathematically for any map that you can draw. The 4-color theorem was proven by Ken Abel and Wolfgang Haken. So the Abel-Haken program, or proof, was using a computer program to go through and literally check every possible example of a continuous graph like this one here. They literally checked every possible example. So they used every arrangement that they possibly could and ended up working out that, yeah, there's actually no way to actually prove it. Or, sorry, there's no way to actually end up with a 5-color requirement for a mathematical graph or map in this particular case. Now, interesting side note about Ken Appel. He taught one of my classes at the University of New Hampshire. At the time, I believe he was at University of Chicago. Nope, University of Illinois at Urbana-Champaign. So 1976, the two of them. Yeah. So anyway, they were. They were at the University of Illinois, Urbana-Champaign, and Ken Appel ended up working at the University of New Hampshire. Where he was a guest lecturer in 2003. Would have been my, yeah. Nope, 2004. So he came into my history of mathematics class that I took in 2004 in the spring. All math education majors were required to take this course, regardless of what level you were teaching at, in order to better understand where mathematics has been, where we're going, get a better understanding of how it all works. And to be a little bit more into the history of our particular subject. I mean, it's kind of important when you eventually get into any particular subject. Like, you really should know more about the history of your subject. All right, so Ken Appel, Wolfgang Haken, University of Illinois Urbana-Champaign, and Ken Appel came to the University of New Hampshire in, goodness, I don't even know when that was, but yeah, he moved to New Hampshire in 1993 and taught until 2003 when he retired as professor emeritus, and then he was called back in by Professor Grinberg, who was our actual instructor for that course, and Dr. Appel was asked to come in for a single lecture to specifically talk about the four-color theorem. So it was very cool to be able to see like somebody who actually came up with something and talk with them. Usually you think about all of these and they're in a very historical context, like, oh, this happened like 400 years ago. No, this happened like, at that point 30 years ago, 20, 25 years ago. And it was just very interesting to start looking at some of this stuff. And again, especially speaking with the person who did the research that we just talked about in class. Yeah, something else that came out from that particular class was my annoyance at the Banach-Tarski paradox and the axiom of choice. It became kind of a joke in our class that axiom of choice was just the answer to everything. I'm not going to get into it because it's not fun for me. And at the age of 80, Ken Appel passed away in 2013, and he was a really cool guy to get to know and just talk with, even just for a few short hours. Um, but yeah, very affable kind of guy and very approachable. So it's one of the as short a time I spent with him, that was kind of one of the things that I wanted to take away from his particular talk was like, I want to be a little bit more approachable than your standard fare mathematician who kind of is very high and mighty, or at least feels that way. All right, so there's other cool stuff that happens with graph theory. You don't always have to have maps that are you don't have to have maps that work exactly in this way, in that they are all individually connected via this blobby format. You're allowed through graph theory to have maps that do end up crossing each other. But this particular type really wants you to make sure that you understand that this particular type of behavior where you're not allowed to cross over or under any particular map, right? That's not possible for this particular setup. Yeah, planar graph. There we go. It's been roughly 10 years since I graduated with my master's, so, excuse me for not remembering a whole lot of this stuff. But planar graph, can't cross. And they're only going to meet at their endpoints or nodes. That's edges. So, can't have any of their edges cross. They can only meet at the endpoints or the nodes, and that is going to be our planar graph. There's also, this is going to be non-planar. Because of the crossing at the center. So planar graphs are an interesting sort. You also get into all sorts of cool stuff that happens. You can get direct graph. What was that? Okay. It's weird. You get directed graphs, which specifically talk about things going from one place to another. And that sort of thing can exist for things like the traveling salesman problem, for example. Uses directed graphs. What happens with the traveling salesman problem is you have a whole bunch of nodes throughout an entire map. And there's not necessarily any particular arrangement of them. However, they are connected in some way that allows you to get from one point to another. And the idea is that you do have connections that you're trying to make. I'm not going to solve this because it has been far too long. Let's leave that one empty for now. And that one. So let's say that this is a map of a particular area wherein you're trying to get to all of the individual cities on this map. You have to use the roads that are given, or airways or something like that. But traveling salesman is implying that you are driving or taking a bus or something like that. You're using ground transportation to get from one point to another. And usually you want to take like kind of the shortest route possible to get through all of the cities in total. So typically what happens is you end up with a path that goes from, let's say this is your start, and then you want to end up back in the same place after you've finished your entire route. So where do you go? Well, in the traveling salesman problem, you have to get through every single city on the entire map, preferably without going through the same city twice, and yep, not possible in this one. I already figured it out. So in this particular case, you're going to have to go through the same city twice. This one specifically, because there is no other way to get into this city from either this one here or this one here, and then go all the way through this city and all of these without going back one of the two ways that you already came. So anyway, one solution to the traveling salesman problem would just be, alright, just like basically pick. Just try to get through all these things best you can. Uh-oh. I didn't leave myself a path back. Okay. So yeah, this is where the problem is. Probably you're going to end up going back through here. Here. Damn. Here, back, over. All right. So this is not an ideal path. However, what you would do is you'd look at this as a directed graph, and you'd say like, okay, in each of these directions, these are the routes I'm going to take, and, right, these are the directions I'm going to take as we go between each one. Now, there could be something like, in one particular direction, there's a toll road somewhere, but in the other direction, there isn't. So, things like that would actually potentially make a difference. What you would want to do is basically create a giant matrix that's going to say, like, to get from city A to city B, we're going to incur a penalty of, like, +2. Whatever 2 is. This is like, you know, you're going a certain number of miles. Maybe A to B is 2 miles. And B to A can also probably be 2 miles. Although it could potentially be more, again, like if you can't go this particular route, or if there's a certain, like, one-way area, or if there's construction or things like that, then you could end up having something that, you know, there's a detour. So you got to go 4 miles if you want to go from B to A. All right, from A to A, from B to B, these are all zeros, so it's not going to help you any. And you're going to get an entire matrix that is built out with every single city connected to every single other city. Now, in the case of getting from, let's say, city A over here to city M over here, the cost to get you there is going to be the shortest distance, let's say, here, 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 and here, all connected. So realistically, you would not take the direct route from A to M. You would not want to take the direct route from A to M because that's not an efficient route. You know, you may end up going that way, but it's not efficient. Anyway, so graph theory is very interesting, and I'm not as well versed in it as I used to be. It was part of our combinatorics class through the master's program that I did, and it's a very, I loved it. You know, doing all sorts of fun stuff with it. And then when we did, I think that must have been the same semester as I took partial differential equations, because I remember doing this around the same time as that. Yeah. Anyway, we talked about, like, Hamiltonian paths, which are things that use all of the paths that are available without repeating. And again, in this particular case, you can't do that. You're not going to end up using all the paths unless you start repeating other paths. All right, anyway. So, for tonight, hadn't really thought much beyond celebration of Ken Appel. Thank you, Ken, wherever you might be. Think that I'm going to do some differential equations tonight, just because, why not? It's fun. Alright, I didn't keep anywhere near as many boards as I thought I did. Alright, let's go back then. Nope. 2. Really? Oh, there we go. 2020. And under... Alright. Alright, the principle of superposition in differential equations is telling us that if y1 and y2 are solutions to a particular differential equation, and the linear combination of the two is also a solution. So in that case, this was typically given as for example, if we got y double prime plus 3y prime plus 2y equals 0, then we have two particular solutions, y1 and y2, which are, y1 and y2 are going to solve this equation. So then what happens is we can say, all right, if we take then the linear combination of the two, what does that mean? So the linear combination of those two things are going to be some constant c times y1, or c1 times y1, plus c2 times y2. That is the linear combination of these two things. So c1y1 plus c2y2 should also, if we plug it into this equation, yield us that we're going to get solutions to this particular thing. So how could we do that even without knowing what the solutions are? It doesn't actually matter. So if we go into this saying like, okay, what is let's call this just y as a whole, all right, y equals this whole thing, then what we can do is say, okay, plug in y into all these pieces. I should probably write this out first. So y1 is going to yield that y1 double prime plus 3y1 prime plus 2y1 is equal to 0, and y2 double prime plus 3y2 prime plus 2y2 is going to be equal to 0 as well. So then if we try to show that the linear combination of these two things is also a solution, then we're plugging all of this in, and we end up with c1y1 plus c2y2 parentheses double prime plus 3 times c1y1 plus c2y2 parentheses prime plus, that's not going to make it, 2 parentheses c1y1 plus c2y2, like that. Totally. Yep, totally works. 100%. Is equal to 0. All right, so this has to come out to be a true statement, otherwise none of this works. So here, when we take derivatives, we're looking at the second derivative of this thing here. Well, this has a plus in between it, so if we take the first derivative, we're going to end up with c1's a constant, so it just gets kicked out, and then it's y1 prime plus, again, deriving works over addition, c2y2 prime plus 3 times the quantity, c1 y1 prime plus c2 y2 prime plus twice c1 y1 plus c2 y2 equals 0. Okay, then here we take a second derivative. So this is going to be c1 y1 double prime plus c2 y2 double prime plus 3 c1 y1 prime plus 3 c2 y2 prime plus 2 c1 y1 plus 2 c2 y2 equals 0. All right, and then we could just rearrange this stuff. So now c1 y1 double prime plus 3 c1 y1 prime plus 2 c1 y1 plus c2 y2 double prime plus 3 c2 y2 prime plus 2 c2 y2 equals 0. All right, if that doesn't look enough like these for you, then we can also factor out a c1 from the first set and leave y1 double prime plus 3 y1 prime plus 2 y1 plus factor out c2 from the other one, y2 double prime plus 3 y2 prime plus 2 y2 equals 0. And now when we look at this, we've got exactly the things that we had over here. So y1 double prime plus 3y1 prime plus 2y1 equals 0. It had to satisfy the equation above, so this is equal to 0. times C1 plus C2 times y2 double prime plus 3y2 prime plus 2y2 is 0. And that's set equal to 0. I think I could probably convince you that this does actually work. So yeah, we get 0 equals 0. And we can therefore prove that the principle of superposition works, at least for this particular equation. I could actually do this more generally and say that this works for any we can generalize to any what is it? Ordinary homogeneous equation. And it doesn't even have to be linear, like this one. Linear in that we have all of the individual y terms have attached to them functions, which are functions in the independent variable only. So these are functions in the independent variable in that they are constant. 3 and 2, and in fact 1 at the very beginning. Right? We have a 1 here, a 3, a 2. But it doesn't even matter. If these had t's, t squared, square root of t, cosine of t, all sorts of complicated stuff, it does not matter. Anything that we do here, we would be able to do over here as well, and show that it's just going to end up becoming the exact same thing. These 3's out front could literally be, you know, what's the usual term for this? It's usually P, Q, and R stuck in front of all 3 of these. So this could be a P, a Q, and an R. And likewise, we go through all of this stuff, and we end up with a function P that is a function of T. So P of T, Q of T, and R of T. We could go through all of this stuff and show that it works for any linear functions or linear equations. And then to prove nonlinear, it's not any harder really. You just have to show that it could be any function based on like anything at all. Takes a little bit of doing, I guess. All right, so that is the principle of superposition. My next thing to talk about would have been, let's see, for my differential equations class, this was LaPlace transforms. So LaPlace transforms are a mathematical tool that is used for forcing functions on differential equations, and particularly for those forcing functions which are discontinuous. So if we have like some sort of impulse force that exists between certain times, so you, like at time 0 you turn on a rocket engine and it increases in force to a certain level so fast that it might as well be instantaneous. Right, realistically, rocket forces, like, you know, can increase to a particular level and then go like this and stay more or less constant. But if this is sufficiently short, then it's roughly equivalent to saying that we had T0 and then it jumps up to whatever your 1 value is for this. So if you had some sort of constant, right, it's going to jump up to this level and stop or stay at this particular level. This also works for, let's see, we said discontinuous. Impulsive. And impulsive often works with piecewise continuous. So a function that, for instance, increases linearly and then stops at a certain value, and then maybe it decreases sharply at... Right, maybe it decreases more as like an exponential, and then it increases like a logarithmic. Right, so stuff like this. Things like this are possible. In fact, they're technically much more theoretically possible than like nice, beautiful curves. You know, something like this might be sort of like what you would find in a real curve, but at the same time it would be kind of hard to describe it. Anyway, the point is that when you're doing Laplace transforms, this ends up being Joseph Louis Laplace, I believe. Oh, Pierre-Simon de Laplace was a French mathematician from mid to late 1700s through the early 1800s. So Pierre-Simon Laplace ended up coming up with, again, helpful uses for these particular transformations. And this particular interval transform allowed him to create a sufficiently useful tool. So the Laplace transform of a particular function f of t is going to be equal to some sort of capital F. We just call it like the forcing function, the Laplace transform on a variable. This is a dummy variable s, is equivalent to the integral from 0 to infinity of e to the negative st times f of t dt, where e to the negative st is called the kernel of the function, and often given as k of st. The kernel can change depending on which particular kind of transformation you're using. We want to use Laplace transforms in this particular case, so that is the kernel that he used for it. All right, so there are a bunch of important pieces that we can talk about in terms of Laplace transforms. So Laplace transforms are going to be linear operators. So linear operators, generally speaking, allow you to take the linear operation of some functions f plus g and end up with linear operator of f plus linear operator of g In this particular case, our linear operator is the Laplace transform. And also, when you take the linear operator of a constant times that f function that we had, then this is going to be the same as the constant times the linear operator on f. And taken together, these allow us to do exactly what we talked about up above, which is that we can find any linear combination. So linear operator of C1F plus C2G is going to be equal to the linear C times C1 times linear operator of F plus C2 times the linear operator of G. So being able to do linear combinations is kind of an important thing in terms of solving interesting equations and figuring out that when we're doing Laplace transforms, we can actually come up with the, again, the principle of superposition comes back into play, where if you find two separate solutions, you know that their linear combination is also a solution. So we just call it the linear combination of these two individual solutions are our total solution. All right. So there are a number of things that we can do with the Laplace transform. So if we start with a function f of t, and this time we multiply it by some sort of exponential, e to the at, this changes our integral that we were taking. So this is going to be integral as we go from 0 to infinity for e to the negative st times the function that we had, which the argument to the linear operator Laplace transform is e to the at f of t dt. Now, if you notice, these are rather nice to use. So here, these will combine. We end up with the integral from 0 to infinity of e to the negative st plus at. So when you multiply exponents with, when you multiply like bases, then what we end up with is summed exponents. So e to the negative st plus at times ft dt. How does that change stuff? Well, this is now going to say that we have integral from 0 to infinity of e to the, here we could actually factor out a negative from this, and this would be a, s minus a parentheses times t at the end times f of t dt. Now, what we saw earlier was that the linear operator, or the Laplace transform of f of t, was going to be capital F of s. And here, what we've done now is our s changed from just being negative st to a negative parentheses s minus a times t. So our s term is now replaced by s minus a. So this says that we're going to get a capital F of s minus a. This is a horizontal shift. So if you remember the horizontal shifting that we were talking about with function transformation, like way back when, this is how this works. How about the Laplace transform of t to the n times f of t? This is going to create, same thing here, integral from 0 to infinity of e to the negative st times t to the n f of t dt. So in this particular case, I don't really have a good derivation for it. However, the idea here is that we would essentially have to do integration by parts n times until this thing eventually works its way down to no t's left over. Well, in doing so, that's going to cause a lot of other problems. And it would eventually work its way down to an alternating sign that would appear, right? Because you're going to do integration by parts. It's also going to start taking the derivative or integral of this particular term. Actually, right, derivative we want of this, or this particularly. We want the derivative of t to the n, and the integral of e to the negative st, possibly times f of t. Or we can leave f of t in there, but either way again. Doesn't much matter how we do it, it's going to cause problems. We're going to need this eventually works itself down to the nth derivative in terms of s of f of s. Yeah, so that's what they're doing. Okay, so they're taking the they're taking the integral of the kernel, which is then going to cause this to keep building, and then taking the derivative of this piece here altogether. All right, there's a whole bunch of other ones. Your instructor probably has a formula sheet for you for all of the Laplace transforms to be able to solve what these individually are going to be. But the ones that you're mostly going to use, if I may be so bold, the ones that you're mostly going to use are going to be things like the Laplace transform of a constant, which is the integral from 0 to infinity of e to the negative st times that constant dt. So what's this going to be? Well, you're going to end up with the constant coming out, integral from 0 to infinity of e to the negative st dt. And then when you take the integral of this thing, this is just going to end up being c times this is a negative 1 over s is going to be your integration factor to try to make this a, for instance, e to the u du. negative st equal u, so therefore oi, du, sorry, equals a negative s, negative s dt. So here we already have a dt, we don't have a negative s. Do not, under any circumstances, divide the negative s onto both sides and be like, oh, well, here you go, I'm going to do this. No, don't do that. In order to get a du, you need to introduce the terms that you have. So what you should do is say that this is going to be multiplied by a negative s here, and then multiplied by a negative 1 over s elsewhere to make these terms divide out to make a form of 1. So negative s divided by s, or sorry, negative s divided by negative s, and then split 1 goes in to make negative s dt, which is du. And the other one is negative 1 over s, which comes out as a constant. In doing so, we end up with here e to the negative st evaluated from when t goes from 0 to infinity. Technically, you can't do that, so you have to take a limit, and yada, yada, yada. Anyway, negative c over s times the limit as t goes to infinity. I guess technically we use a constant here, but I always hated this part. A goes to infinity of e to the negative s times a. And then we are subtracting what happens when you plug in 0. So that's going to be e to the negative s times 0. This is going to end up being negative c over s, due to the fact that this one here is going to be a 1. Oops. No, that's a positive. Yep, this one here is going to be a 1, and this one here is going to be a 0. You have an infinity that's going in up top here. E to the negative infinite number is going to be 1 over a very, very large number, so it's going to 0. So 0 minus 1 gets to a negative 1, so negative c over s times negative 1 gets to a positive c over s. Again, if I may be so bold, this is going to be what you're seeing almost all the time. Something with constants, something pretty easy. And I will probably contradict myself within the first 2 minutes of doing an example. So, what about the LaPlace transform of t? It's going to be the integral as we go from 0 to infinity of e to the negative st times t dt. Okay, again, integration by parts. What we can do here is say that e to the negative st dt is going to be our integral portion, or the dv that we want, whereas t is going to be the u that we want. So du is just going to be equal to dt when we get there. We know that dv equals e to the negative st dt. So v therefore must be equal to, that's going to be negative 1 over s, just literally what we just did up there. Why am I looking? Negative 1 over s times e to the negative st. So integration by parts, we're going to get u times v, right? It's just literally the t times negative 1 over s e to the negative st. This is going to be evaluated as t goes from 0 to infinity, and that is just the v portion? Yeah. No, all of it will. Minus the integral from 0 to infinity of v du. So negative 1 over s e to the negative st times du is just dt. This negative 1 over s comes out as a constant. This stuff here gets evaluated. Again, we're going to end up with the same basic limit that we did up top. The only problem is now we have a t that's also going to be up top. So this is the limit as t goes to infinity of t over e to the st. And then we also get an s and a negative sign, which are going to be in there as well. Okay, minus 0. So we plug in that, we get 0 times e to the 0. So it doesn't really matter, this is all just 0. Then in here, we're going to get a plus 1 over s times the integral 0 to infinity of e to the negative st dt. Which again ends up being 1 over s times this integral is again going to be negative 1 over s times e to the negative st, and that's evaluated from 0 to infinity. T goes. All right, this one here, the limit as t goes to infinity of a linear function divided by an exponential function. The exponential function is going to infinity a lot faster than the linear function. So this is going to end up with an indeterminate form, technically 0 over infinity. Oh, nope. No, never mind. They're both going to 0. It's fine. So they're both going to 0. It's just 0. This one now is a negative 1 over s squared. And then we have the same deal that we did before. This is the limit as t goes to infinity of e to the negative st minus e to the 0. A negative e to the 0 is just going to be a minus 1 again. Man, shoulders kill me today. And here we have, this is going to infinity, which again is going to make this negative infinity. E to the negative infinity is 0. So all of this is gone again. All of this is 1 again. Should have switched. Right? If we were to look at this in terms of the previous one that we had, oh no, okay, I got it now. Yeah. I'll show you the other derivation in a second. So here, yeah, this is going to be a negative 1 times negative 1 over s squared, so that's just going to be 1 over s squared. This is the LaPlace transform of t. So, coming at this the other way, which is why I was confused for a second, if we were to look at this as the LaPlace transform of t to the first times the constant f of t being 1, then what this is going to be is a combination of these two things here. So we end up with negative 1 raised to the nth power, which is again the same as what was on the inside there, so that's 1, times d ds, so the first derivative of the Laplace transform of what we had up here. Now this c value here, again, is 1. So this, translating all the way down, is going to be c over s is 1 over s. So we're taking the first derivative of 1 over s with respect to s, and then multiplying by negative 1. This is why, when we take the derivative with respect to s, this is going to be s to the negative first, so we bring down a negative 1. And then the power becomes a negative 2. So this is now going to be a 1 over s squared. Alright, so these corroborate each other, which say that, yeah, we're going to get that as our answer. Alright, so now let's apply it. Maybe I should do a trig function one first. Alright, I'll do one, just because it's in my notes and it's easy enough. So what happens when we take the Laplace transform of the sine of at? And you know what, I'm going to turn it into bt because this is what I do for my function transformations. A is for amplitude, b is for your frequency. So this is going to be integral from 0 to infinity of the kernel e to the negative st times the function sine of bt dt. Again, we're going to have to do integration by parts. And again, we're going to want e to the negative st dt to be equal to dv. And so therefore our v is going to be negative 1 over s e to the negative st. Yep, cool. And then we're going to want the rest of it, which is the sine of bt, to be equal to u, which means that du is going to be equal to b cosine of bt. bt. dt. All right, so do integration by parts on this, and we end up with uv, so again, these two pieces, so negative 1 over s e to the negative st times the sine of bt, bt. Evaluated, t goes from 0 to infinity. All right, minus integral of v du. So v is, again, this piece, negative 1 over s e to the negative st times, what did I say? Du. B cosine bt, dt. This is an ugly mess, so we're going to remove all the constants. They're going to kick out front. This stuff here is going to end up doing the same thing as we did up above. The limit as t goes to infinity of e to the negative st, it's technically negative 1 over s here too, okay, times the sine of bt minus a negative, it's going to make plus 1 over s e to the negative, nope, e to the 0 times the sine of 0, right? Plug in zeros for t's. This stuff is all going to be 0 because the sine of 0 is 0. E to the 0 is 1, but again, sine of 0 is 0. So that's all multiplied to 0. over here, this becomes a little bit interesting. You do see that the sign of bt for any particular value will always be between -1 and 1. But then e to the -st as t approaches infinity is going to become 0, no matter what. So we got this value that's between -1 and 1, and we don't know where it is as we go off to infinity, but then we're just multiplying it by something that's going to 0. So it's eventually going down smaller and smaller and smaller. So this whole thing is all 0 again. All right, then here, this is going to be a plus 1 over s, and in fact that's b over s, times the integral of e to the -st cosine of bt. I'm going to keep doing that. bt dt. And this is now equal to the original that we had up here. The integral from 0 to infinity of e to the -st sine of bt dt. All right, now we're not going to use that just yet, but we're getting there. Now we have to do integration by parts again. This is why I just went, All right, you oftentimes have to do integration by parts multiple times in order to make this work at all. So for this one, we're going to let e to the -st dt be our dv again, which means that our v is again going to be -1 over s e to the -st. All right, same thing. Then that also means that our, nope, not sine, cosine of cosine of bt is going to be u, which then makes du equal to negative b sine bt dt. All right, so when we take that, this is all 0, so we can ignore it. Now we get a b over s out front. This is going to be the integral. Nope, sorry. This is going to be multiplied by uv, which is going to be -1 over s e to the -st times cosine of bt minus integral from 0 to infinity, and this is also evaluated t equals 0 to infinity. All right, of v du, so -1 over s e to the -st, and times du is going to be a negative times a negative b sine of bt dt. All right, this has 3 negatives attached to it. So let's just get rid of those 2 to begin with and get that out of the way. This is then going to be a negative here. This ends up with the b over s multiplied by this evaluation here. Again, has the same sort of resolution as what we had up above. As we take the limit as t goes to infinity of -1 over s e to the -st times the cosine of bt. Again, cosine is between -1 and +1, so it's indeterminate what its actual technical limit is, but you know it's bounded. Then e to the -st as we go off to infinity becomes 0 again. So this whole thing is just 0, yet again. Then we have a minus, and now we plug in 0 for all these things. So, just want to make sure I'm not making some weird mistake. It's been known to happen. Okay, So we plug in 0 for all of the t's here. This is going to be a negative 1 over s times e to the 0 times the cosine of 0. Cosine of 0 is 1. E to the 0 is 1. These are all gone. These are all 1. This is now going to be 1 over s. This is b over s still, multiplied by the entire quantity. Then we have these here. So now we have an integral where we're going to subtract out. Something doesn't look right. I feel like I'm going to cancel something out, and that's going to be a big mistake. Let me just double check my notes here. This is the other problem. I wasn't checking my notes all the way through. Oh, yeah, we're good. Jeez. Okay, we're not going to do this because that's, again, just another integration by parts. We don't want to do that again. This is just minus the integral from 0 to infinity of 1 over s e to the negative st times b sine of bt dt. All right. This is then b times s times 1 over s minus, again, this is a double negative here, makes these become positive. This is going to be a minus b over s integral from 0 to infinity of 1 over s e to the negative st times b sine of bt dt equals integral from 0 to infinity of e to the negative st sine of bt dt. All right, now we can take this integral here and shift it over. That's right in the way. I am literally right in the way. Right there. Okay. So this is now one of these integrals, and this is adding another b over s to this integral. So this is 1 plus b over s times the integral from 0 to infinity of e to the negative st sine of bt dt equals b over s squared. And then just the integral from 0 to infinity of e to the negative st sine of bt dt, the original thing we wanted in the first place, is going to be equal to then b over s squared times 1 plus b over s. Which why don't I feel good about that? Okay, that was b over s squared. We had that. Should it have been negative? Allegedly. Huh. LaPlace transform table. Let's just double check this because, yeah, I don't want to be wrong. That would be rather embarrassing. Sine. I got it. Okay. Oh, I did forget this, however. This is a b over s times a 1 over s. So this should be a b over s squared, which is going to be b over s squared here. Okay, which is b over s squared plus b. Why isn't that squared? That should also be squared. Alright, how do I screw that up? That b. Okay, let's put that in red. b 1 over s. There we go. Oh man, it's been a long week already. So, b squared over s squared there. And this is going to be a b squared over... Nope. That's still b. This one's b squared. B squared over s squared. Alright, so then the eventual solution that we got here is that Laplace transform for the sine of bt is going to be b over s squared plus b squared. Alright. So putting it into practice is a little bit more difficult, but it's worthwhile. So as we get into differential equations, the Laplace transform of the nth derivative of f of t is going to end up being s raised to the nth power times Laplace transform of f of t minus s sub n minus 1 times f at 0 minus s sub n minus 2 times f prime at 0 minus, and then this continues until we end up with s times the n minus second derivative of f at 0 minus f n minus first derivative at 0. So these are just the initial conditions here. Generally speaking, we don't have to worry about them too much, or they're going to be given as zeros most of the time. So so if we ended up with y triple prime plus 3y double prime minus 6y prime plus y equals the sine of 2t. Then what we could do is use Laplace transforms to figure out the solutions to this entire problem fairly easily, not always 100% easily, but at least, you know, it's sort of decent. Yeah, I probably should have picked a better... Probably should have picked a better polynomial for this. wasn't good. Yeah, that was ugly. Okay. Let's do this. I am now engineering a problem to be much nicer. So this is going to be 3 y triple prime plus 4 y double prime minus 43 y prime minus 84y is equal to sine of 2t. Okay. So the way that this works is if we want to be able to solve this particular differential equation, we can take the Laplace transform of all of, well, we take the Laplace transform of the whole thing. But if you remember, the Laplace transform of all of this stuff is going to be individually we're going to get 3 times the Laplace transform of y triple prime plus 4 times the Laplace transform of y double prime minus 43 times the Laplace transform of y prime. And let's make the caveat here. All derivatives of y are 0 at t equals 0. Okay, and minus 84 Laplace transform of just y. It's equal to the Laplace transform of the sine of 2t. Well, we just did that on the previous page. So this is going to end up being the Laplace transform of the sine of 2t is 2 divided by s squared plus, this was 2 squared is 4. All of these end up becoming 3 times the Laplace transform of y triple prime is going to be y to the third minus, and then in this particular case we would have had, no, sorry. This was s to the third times y. All right, the Laplace transform of little y is just usually listed as capital Y. All right, so s cubed times y minus, this would have been then s squared times y at 0 minus s times y prime at 0 minus s squared, nope, minus y double prime at 0. Now, all of these, again, are going to end up being 0. We're going to call it all function values, all derivatives, including 0th derivative. These are all just going to be 0. So those all go away. Similarly, on the next one, this is going to be 4 times the Laplace transform of this thing is going to end up being s squared times capital Y minus s times y at 0 minus y prime at 0. Which again, these are 0. Minus 43 times the Laplace transform at y prime is going to be s times capital Y minus just y at 0. Again, 0. And then minus 84 times big Y. Excuse me just one second. Alright, so then this is going to be equal to twice over s squared plus 4. Now from all of these, the 0 portions just all drop out, and we end up with the polynomial, very conveniently, 3 s cubed, factor out a y from all the terms, 3s cubed plus 4s squared minus 43s minus 84 equals twice 2 divided by s squared plus 4. So now we have a polynomial here that we can factor. And, alright, this is pre-calc level, so maybe I could just do this real quick, but just use Wolfram Alpha, it's fine. But you may also, it's a good exercise to at least go through it and say, alright, what is this going to be really? One of the ways that I do it is punch it into your calculator real quick, figure out approximately where they are, and then get the zeros of this particular function, or at least approximately where they are. So this is going to be 3, 4, negative 43, negative 84 using synthetic division. Negative 3 and positive 4 are going to be the easy zeros. So a negative 3 is going to make this 3, negative 9, negative 5, positive 15, negative 28, and we better hope that this comes out to 84, so yeah, 84, 0. And then 4, it's going to end up being 3, 12, 7, 28, 0. So then here, this is our last one, 3s plus 7. This is going to be s plus 3 and s minus 4. So our y is going to be equal to, let's hope I'm not blocking, not yet, okay. Y is going to be equal to, we can drop all these, and in fact they're factors, underneath at the bottom on the other side. It's going to be 2 divided by this huge thing here. So this is going to be s plus 3, 3s plus 7, s minus 4, and s squared plus 4. Now, let's not shy away from this. We've only got 8 minutes until Jason Charles Miller starts, but nonetheless, we can do this. All right, so we're going to do partial fractions here to split all this up. Yes, I did just say partial fractions in 8 minutes. Sure, that's going to happen, right? So, 2 divided by all these things is going to be equal to a over, s plus 3 plus b over 3s plus 7 plus, this looks too much like a 5, but we gotta suck it up for now, c over s minus 4 plus, this one is a little bit awkward. Remember that because it can't be factored into nice terms, or rather the terms that we're going to have are like imaginary, so don't do that. In theory you could, but yeah. What you'd probably want to do here is have a linear factor up top and make this ds plus e, I guess. Keeping in mind, right, these are all, this is not the constant e, this is actually the, so let's just grumble about it for a little bit, that's fine. This is why I use capital letters when I'm in class. A, B, C, and ds plus e divided by s squared plus 4. When we multiply all this over, this is going to end up being a 2 is equal to everything except s minus 3. So 3s plus 7, s minus 4, s squared plus 4 times a plus. everything except 3s plus 7. So this is going to be s plus 3, s minus 4, s squared plus 4 times b plus. S plus 3, 3s plus 7, not s minus 4, but s squared plus 4 times c plus s plus 3, 3s plus 7, s minus 4 times, parentheses, ds plus e. So one way to resolve this is multiply everything out and eventually end up with yep, multiply all this out and you're eventually going to end up with a certain number of terms which are 2, 3, 4, s to the 4th, certain number of terms which are s to the 3rd, certain number of terms which are s squared, certain number of terms which are s, and a certain number of terms which are constants. When you do that, you're going to end up with each of those equations set equal to 0 with the exception of that last one. The constant is going to have a function value of 2. So all the rest of them, s's, s squareds, s to the 3rds, and s to the 4ths, have to be equal to 0 because we don't have any on the left-hand side. There aren't any. So I'm going to do what my students do. This is going to be awful. It's probably not going to work. Nope. It only goes that way. That's terrible. Okay. It's going to be like, what are you doing? This is way too far away. I can't see that. Yeah, anyway. Not so much. Oh well. Okay. So I am going to plug this into, everybody's going to hate this, woohoo. Oh. Alright, 3s plus 7. Not the second one. Into the 3rd and into the 4th. S plus 3 is going to go into the 1st, no, the 2nd, the 3rd, and the 4th. minus 4 is going to go into the first, and the second, not the third, and then the fourth. And s squared plus 4 is going to go into the first, the second, and the third, but not the fourth. Alright, let's see if this can actually simplify this, because this is going to be pretty ugly. Come on, Wolfram. Whew. Okay. Nope, that looks perfect. Awesome. Okay, so we get 2 is equal to 3a. This is all going to be the s to the fourth term. So all s to the fourths are going to be 3a s to the fourth plus b s to the fourth plus 3c s to the fourth plus 3d s to the fourth, and e does not get it. E does not get up to s to the fourth. Alright, plus s to the third is going to be a negative 5a s cubed negative b plus 16c plus 4d plus 3e s cubed. Okay, plus s squared is going to be a negative 16a plus, nope, minus 8b. Put it on the previous line. It's terrible. That shouldn't do that. Plus 33c. And I get why they do it. It's just terrible. Should be a plus and then a negative on the other one if they want to do that. A minus 43d plus 4e s squared. Plus a negative 20a minus 4b plus 64c minus 84d minus 43e times s plus the constants, which are going to be negative 112a, parentheses there, I guess, minus 48b plus 84c D doesn't have a constant term, and a minus 84e. Alright, so now this is a 1, 2, 3, 4, 5 by 5 system of equations. Again, 3a plus b plus 3c plus 3d must be equal to 0 because we don't have any s to the fourths on the other side of this equation over here. So all this stuff times s to the fourth is going to be equal to 0 s's to the fourth. Similarly, for negative 5a minus b plus 16c plus 4d plus 3e is s to the third, which is equal to 0 s to the thirds from the other side. a negative 16a minus 8b plus 33c minus 43d plus 4e s squared must be equal to 0s squared. Negative 20a minus 4b plus 64c minus 84d minus 43e times s is going to be equal to 0 s's. And a negative 112a minus 48b plus 84c minus 84e. You know what, let's move that over. Minus 84e equals 2. Because again, this is the constant term. I would never recommend doing a 5x5 system of equations by hand. That's horrible. So instead you can use matrix methods, you can use row-reduced operations, again if you really feel like doing it by hand, or you can just do row-reduced echelon form for all of it to make sure that you actually are going to get this correct. So row-reduced echelon form, we need this to be man, it's been such a long time. All right, matrix, edit, ABC, yeah, okay. So this is going to be a 5x6, which is going to have coefficients reading across and then down, 3, 1, 3, 3, 0, 0, negative 5, negative 1, 16, 4, 3, 0, negative 16, negative 8, 33, negative 43, 4, 0, negative 20, negative 4, 64, negative 84, negative 43, 0, and negative 112, negative 48, 84, 0, negative 84, and 2. So if we take the row-reduced echelon form of this particular matrix, we're going to end up getting, and let's see if we can get this in a fractional form. I'm sure we could, in theory. Oh, that's ugly. All right. A equals 1 over 91. B equals negative 81 1615ths. C equals, this one actually ended up getting that's fun. This one ended up getting something times 10 to the negative 4th, so it's refusing to do the fraction version of it, but we'll see if I can get this in another form in just a second. 11 over 2210 for D, and E is negative 2 over 221. All right, so let's see. See if we can get this in a nicer form, and then turn it into a fraction. Boo. Still says no. Whatever. So if we did multiply by 10,000. If we had multiplied by one of these other numbers, maybe it would have worked out nicer. Sorry. Aha, got it. Alright, so this is 221 over 133 times 2210. So is this just really 1 over 1330? It is. Alright, so apparently it was having problems with 1 over 1330. Whatever works, right? Oh. Technically it's off by just a little bit. That is aggravating. Okay. Hey Matthew, how's it going? Oh, it's ugly. Oh man. It's trying to solve for the fourth roots and then going through the fourth root equation, or the fourth degree polynomial solution equation. Oh man, that's ugly. Alright. Hey, whatever. No problem. I've been doing some differential equations because nobody came in. Because I enjoy this more than, or I haven't done it in a while, so I'm enjoying it more than random other stuff that I could have been doing. All right, so this is actually technically approximate, and we're just going to deal with it. So, sucks to be me, but hey, whatever, it works. So the differential equation that we're getting, or the solution to the differential equation we're getting here, is that y is equal to this stuff. So then now we have this whole equation here, which is going to be y equals, a is going to be 1 over 91 parentheses s plus 3. Minus 81 over 1615 times 3s plus 7. C is a positive 1 over 1330 times s minus 4. Again, we're hoping that's the equation. That's the constant for it. All right, plus d is going to be an 11 s divided by 2210 times s squared plus 4, but then we have a plus e, which is going to be here, minus 2 divided by 221, and then we're going to multiply both top and bottom by 10. So it's going to be a minus 20. Whew. When we get all this, then we have to do the inverse Laplace transform of y, which is just going to get us y. Then we're going to take the inverse Laplace transform of each of these pieces. Now again, this is a linear, whatever the thing is. This is a linear operator, so we can take out the constant multiple here and make this 1 over 91 times the Laplace, inverse Laplace of 1 over s plus 3. Minus 81 over 1615. And actually, technically we should also take the 3 here. So this is going to be, factor out a 3 with the 1615, divide out from 81 is going to be 27 over 1615 times the inverse Laplace of s plus 7/3. Plus 1 over 1330 times the inverse Laplace. Yeah. Of 1 over s minus 4. And this is, technically I'm just going to do two steps here at once. We're going to divide here and divide here as two separate portions, separating on the negative up top. So then this is going to be an 11 over 2210 times the inverse Laplace of s over s squared plus 4 plus, actually that's going to be a minus, 20 over 2210 again is going to be a 2 divided by negative 2 divided by 221. So it's just basically re-simplifying what I just unsimplified. And that's going to be, actually we need that 2. We need that 2 on the inside. It's going to be 2 over s squared plus 4. So we need to get rid of the 2 that came out here. And just make it a 1. Alright, when we take the inverse Laplace of all these individual things, this is going to be completely insane, so bear with me. Alright. So, let's get the Laplace transform list back up, just so I don't make a mistake. It's been known to happen quite a lot. Here we go. So inverse Laplace on this is going to be 1 over 91 times inverse Laplace of 1 over s plus 3 is going to be e to the, technically this is going to be a negative parentheses negative 3t, so e to the 3t. 1 over 91, e to the 3t. Alright, minus 27 over 1615. Inverse Laplace of this thing, sorry, that's 1 over, yeah, is going to be e to the, again, this is going to be a negative parentheses, negative 7/3 t. So down here is a negative 27 over 1615 e to the 7/3 t. Plus 1 over 1330. Again, this is the one that's giving us issues, so it potentially might not be. Times e to the 4t. But it's going to be pretty close to that. Plus 11 over 2210. Inverse Laplace of this thing. This, interestingly enough, is basically the same as our sine that we found up above, but this one is going to be the cosine of 2t. And then we get a minus 1 over 221 times, this is the sine of 2t. That's all the stuff we were doing before. So then we just need to rewrite. Plus 11 over 2d210 cosine of 2t minus 1 over 221 sine of 2t. Alright, so this is the total solution for all of it. Now, it may be interesting to note, for those of you who are more interested in this sort of stuff, the original differential equation was a third order differential equation, and there are 3 homogeneous solutions. So, y1, y2, and y3. If you plug any single one of them into the original equation, so that was way up here. Here are 3 y triple prime. Oh man. Alright, 3y triple prime. Come on. Here we go. Plus 4y double prime minus 43y prime minus 84y equals 0. Alright, these are going to be the solutions to that particular, or to that homogeneous equation. It's terrible because I was zoomed out and I tried to keep the same resolution. Okay. All right, and then over here, we get the particular solution. Solutions, technically. Because again, either one of these could be plugged in to the original here. Nope, that's a false. That's false. You have to plug in both. When you plug in both of them, you end up getting this stuff is all equal to the sine of 2t. Because that was what I said originally, right? Yep, sine of 2t. Gotta be careful. Don't want to get myself in trouble. Done it before. Students get terribly confused. So anyway, 3y triple prime plus 4y double prime minus 43y prime minus 84y. It's It's going to be equal to the sine of 2t. All right, and again, with our homogeneous solutions, red, with our homogeneous solutions, we have the principle of superposition. Differential equations. Towards the end. So the principle of superposition is going to hold in this particular case, wherein any one of these, like C1 times e to the 3t, C2 times e to the 7/3 t, and wait. Oh, you jerk. Hang on. Oh, they did plus and... man, why did they do that? That's awful. Okay. So it is actually... This is not what I wanted. That one. That one. Yeah. So this should be a negative 3t. Should be negative 7/3 here, and this should be a 14. Okay, we're good. So in fact, any constant multiple of e to the negative 3t, any constant multiple of e to the negative 7/3 t, and any constant multiple of e to the 4t is going to render our original differential equation equal to 0. You can actually go through it if you feel like it. And put in, literally C1 e to the negative 3t, plug it in, get all the derivatives, and they're all going to come out to 0. Or you could do, again, this particular selection, these particular constant values. If we plug all of them in, it also works, of course. And then, again, these particular values for the cosine and the sine end up getting you just one sine of 2t when you plug it into the differential equation. And it ends up being that this is the only one combination of these two things that is going to work in this case. Oops. Any other combination when you plug it into this differential equation here will not get you one sine of 2t. It'll be some other fraction. Alrighty. Have any questions tonight, Matthew? Should have also updated the description. I hit update. Doesn't mean it did it. Oh, I didn't mean about this. I got you. Oh, nice. Yeah, I've got... Unfortunately, yeah, sometimes it does that. So, my dad was really big into woodworking, or still is really, but he doesn't have much time to do it. He's going to be moving back up to our original home in New Hampshire, and he has a wood shop that's there, so he's going to get back into that. And I think He keeps telling us that he's gonna make bookshelves for my daughter, but quite frankly, have yet to see that. Anyway, no, 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 it'll be fine. Hmm. Yeah, he was he was originally a customs broker and hated it. Knew that he was going to be dead by the time he was 50, and he was like, "All right, well, screw this. I don't want to do it." So he had been doing woodworking as a hobby, and then just made it his full-time job for a while, and paid the bills. That was about it. But he loved it. That was the important part. And yeah, went to work and did some. Yep. Yeah, I've got a stack of 2 mouse pads that are sitting on top of. So my desk is not like a gaming desk by any chance, and the surface of the desk is kind of high and forward for the chair I have. So I actually took one of the drawers out from the side and then turned it upside down. So there's nothing in it. It's just an upside down drawer, stuck it about halfway in, and then put the mouse pads on top of it. So it's sometimes it cuts a little bit into the wrist, but it's okay. It actually works pretty well. Of course, mine I don't have the groove problem. I've got the it's just a very narrow amount of space. So like I have the space of the mouse pad. That's about it. Hmm. I do like using the controller for like some games. FPSs though, like I can't do it. I need mouse and keyboard. Or Elite Dangerous, right? Like on my Elite nights, I'm using an old stick and keyboard, and that works fine for 90% of what I'm doing. Yeah, I've got the same for what is that? Control. Did you find anything? Yeah, proof for irrational roots. It's always fun. Well, yeah. Go for it. Okay, so take the natural numbers, go through one at a time. So we're doing like basically a proof by induction. So how do you know that the square root of 2 isn't some other kind of rational number with very large numbers both top and bottom? So like if I went nah, what's root 2? Oops. Square root of 2, so 1.41421356. If I just went that far, and say, give me the fraction for that. No. Okay, cut out. Man, really? I don't have to go that far. Anyway. So square root of 2 could be approximated by like 7071 over 5,000. That'll at least get you the first 4 decimal places. You know, it's not super great, but it's a start, for example. So like, how would I prove that this is not actually? I mean, you and I know it's not going to work, but... Okay. So... Well, hang on. That is contradiction. No, you probably didn't actually stop there, but... I guess I'm struggling to see where you're coming from with trying 1 and 2, like plugging 1 and 2 into where? Alright, so set up two groups, multiply by each other. Yeah, so 1 times 1 is 1, so that's not equal to 2. 2 times 2 equals 4, which is also not equal to 2. So it says that the square root of 2 must be between 1 and 2. Yeah. So are you saying that? Let the square root of 2 be some sort of fraction? I mean, this only proves that it doesn't prove that it's irrational. This only proves that it's not a whole number. I guess my problem is I'm not seeing how this differs from the original proof by contradiction, which says that, okay, a over b is a simplified fraction, which when you square it you get 2. And then let's show that, either way you end up with an unsimplified fraction. So therefore, a over b cannot be the representation of it. It can't be a rational number, and therefore it's an irrational, or it's a new type of number, which we know is irrational. Oh, okay. Yeah, so the assumption was that a over b is a simplified fraction, and that therefore a squared, this stuff being true, makes a squared equal to 2b squared. And therefore, because we have, because a and b form a rational number, a and b individually must be integers. Which, if they're integers, they're closed under squaring. So this is also an integer, and this is an integer times 2 equals a squared. So therefore, a squared is even. And there's a lemma which says that if a squared is even, a is even. Off the page, whatever. Which then means that a is even. So therefore, a can be written as 2k, where k is an integer. I mean, yeah, but you got to prove it. You got to prove that it works for all possible numbers. And just kind of hand-waving and saying, yeah, that works for everything. You don't... So my all right, so let's go back up here. So you're saying, right? You're saying that this is to be two numbers that need to be multiplied together to get you 2. They have to be the same thing. Therefore, it can't be an integer. Therefore, you need to have a fraction, which is rational numbers, if it's going to be a rational number, which then you make it as a over b, which when you square it is going to get you 2. So then a over b, when you square it, are you saying that this is because it has to be over 1 in order to make this over 1? Well, sure, 4 over 2 can be a whole number. I know. No, you're saying simplified. So, yes, in theory. The problem is that when you're looking at something like this, and you're saying, okay, if a over b is a simplified fraction, and when you square it, you get a squared over b squared can't be 1, so therefore, how are you getting 2 over 1? Essentially, but it also doesn't... It doesn't build off of what is previously known in terms of like formal proof. So you have to watch out where it's coming from. I'm not a proofs teacher, so I mean it's not going to help, but yeah. So the rest of this stuff goes through like formal logic to make sure that all of the possible eventualities are taken care of all at once. So it's not just like one little thing. It's trying to do it in terms of like all of them. Because I think, in fact, you can do this for literally any number you want, like any root that you want. I'm going to have to ask the people who are in charge of the proofs course at my college and see if there's something in particular that we're like not... What is it about this that is not going to be acceptable? Because there's something that's missing here, and I can't put my finger on it. No, I mean, nobody was saying it had to be perfect. Um, so I think, according to my users page here, thank you to... Apologies ahead of time. Hi, Euclid. Lexa8774. Matthew again. Thank you. And Rogue Girl. So I think the four of you either are or were here at some point. Thanks for coming in. If you have any questions, please let me know. My name is Obi-Wan Pez. This is N Simplex Pachinko, my Pachinko Hall. And the stream name itself is explained in one of my videos from way back when. But basically it has to do with a bit of research that I did that has to do with the Pascal-Liouville and Al-Jayani triangle, which is the one that starts 1, 1, 1, 1, 2, 1. And as you go down, you just keep adding numbers in different cells to get the next ones down. So the next one here would be 10, next one here would be 10, next one here would be 5. 5 and 1, and a 1 also on the other side, way over there, which you can't see. Hooray. There. Anyway. Yeah, the concept is here. I think I'd like to ask my... Yeah, phone a friend. And try to figure out how it is that this is not going to be the way to just say, like, oh look, it's not an integer. Oh look, now it can't be a fraction because we can't get an integer out of a fraction squared. That isn't, again, that isn't already simplified. And therefore it must be a new type of number. Well, anyway, it is interesting to think about. I am going to be heading out unless anybody has any other types of questions. Let's see. I think I have somebody else that I'd like to follow, or I'd like to, well, it can't be negative because squaring it makes it positive, so yeah. No, it's tomorrow she's on. Okay. Oh, wait. That is tomorrow. Oh, man. So, I would like to raid Edriosa, but she is not going to be on for another 6 minutes. So, we will still discuss more. At least for a little bit. Right. So what happens when you start going into, like, even just -4? Yes, so I could be considered a unit in a secondary form of number, which Gauss hated the term imaginary and decided that he would rename, rather than real and imaginary in the 2D plane, he said, no, this is stupid. These numbers over here are going to be called direct. These numbers over here are going to be called inverse. And these numbers here are going to be called lateral. And it might have been like lateral direct and lateral inverse, but still, same idea. So Gauss decided that these names were much more appropriate for the numbers, just in general. There is a video series on YouTube of 13 videos called Imaginary Numbers Are Real. I highly recommend it. Yeah. I've probably also hyped it on this channel before. So the idea is that yes, you can use imaginary numbers to call them I, which therefore is, when you get I squared, it's going to be equal to -1. Ish. So the problem yeah, so if you were to use the polar form of complex numbers, so when you do rectangular, you're talking like x plus iy, where I is the number which when you square it you get -1. But the polar coordinate system for complex numbers makes actually much more sense. But you gotta understand trig pretty well in order to do it. So polar form, you're basically looking at doing a compass course. You need a bearing, and you need a distance. Your distance is going to be the r value, or the radius that you're going to go out, and the bearing is going to be your angle, or the theta value, around the unit circle. So another reason that, or another method that you could think of them as in terms of rectangular numbers, is that they are vectors. And if you do it with rectangular numbers, basically you're looking at this as you're going A in the x direction plus B in the y direction. Mm-hmm. Right, and because they're orthogonal directions to each other, or technically affine, right? The coordinates are like specific directions compared to each other. They don't have to be at right angles. They can actually be off that way. They can actually be off from each other and be like two angles like this, rather than exactly orthogonal. But right, you consider them different dimensions. So it's a bit like if you were trying to change the color on your television and you had the RGB inputs on the back. Changing the R input is not going to affect your G or B input. So changing the red terminal on your display will not affect the green or blue colors by itself. Like it'll look more green or blue because you're sapping out the red, but that's not really the point. You know, you still have the same amount of the other two colors, it's just that you don't have any more red if you take that out. Yeah, also. So if you're looking at like figuring out what the inverse of a particular number is, then you're going to find that number in the negative direction of the same number you started with. Yeah. So we go over this way and that way, tip to tail, in order to make a vector, which itself has a radius and an angle from 0. Or you could think of it as A in the x direction and B in the y direction, as long as they are an affine coordinate system. Yep. So if you're doing it as 3 plus or 5 plus 3 equals 8, then you're looking at exactly, you're doing it as vectors. Well, this is 3 in the x direction and then 5 more in the x directions, then you just get out 8. Yep. And when you subtract them, yep. You could think of it as 3 or 8 minus 3, or you could do 8 plus a negative 3. So now it's in the inverse direction compared to where we started. Yep. All that good stuff. Matthew, where are you in terms of mathematical classes? I forget. Well, yeah, but like where... I guess... Where was your formal education stopped, and then where have you gotten? I mean, you've gotten through some algebra. I just don't remember exactly where the cut was. Oh, there, that's, yeah. Yeah. Okay, so trig is not an issue necessarily. Yeah, I was just like, I don't know how far I want to get into this, but anyway. Yeah. So if you're taking these as vectors, you could do it with polar coordinates instead, as the red ones here, the r and theta. And then when you start looking at... Yeah, we didn't have a math club at our school. It was like, you're either on the math team or you're not. To do like competitions and stuff. So... Of course, that was a long time ago. Yeah, so when we're looking at this, your vectors, you can either do, yeah. Yay, matrices. So when you're doing like rectangular vectors, then you're doing stuff like, okay, this is going to be a1x hat plus b1y hat plus a2x hat plus b2y hat. Addition and subtraction end up just being super easy, because you're saying, okay, the stuff in the same direction have the same units, and anything else don't have the same units, so you can't add them together. So you just end up with a1 plus a2 in the x direction, and then b1 plus b2 in the y direction. So this is less interesting, but nonetheless something you like need to have a grasp on before you get the next stuff. And you know, same for subtraction. You're just combining like terms. When you do multiplication, it becomes a little bit more interesting. But then you start getting into like, what does it mean to actually multiply the directions together? So, yeah. Khan Academy used to have a nice, like, pictorial web of how all the subjects are connected to each other. And, I mean, not necessarily every connection that exists, but, like, you should complete this stuff before you go on to, like, this stuff over here. And it's not necessarily 100% of it, but, that's kind of the progression that the classes go, at the very least. So, you can always just learn whatever interests you, as you know. Now, hang on, do you mean mathematicians or math teachers? Because there's a difference. All right, go ahead and qualify the statement. It kind of depends, right? It's not necessarily always going to be the easiest path for everybody, right? And right, since you haven't hit a wall, it's kind of like clearly you have more to actually like you have more motivation to just keep going until you either decide you're done or or until you really struggle and then are like, okay, now I need some actual like I need to talk to somebody about this. Like I would love to be able to just take a like cohort of students and have them for 4 years and just be like, all right, all of you, you're coming with me. We're starting from zero. Let's strip everything away. Forget what you know. Here's what you actually, let's build mathematics off of itself and see what you can actually get. That, no, you don't know that yet. You can't use it. Addition? What is that? Define what addition means. And like you said, it's gonna really be like the students who are the most motivated and the most interested in mathematics who are going to be the ones who really get it and really move in on it. But I mean, that's also what abstract algebra is for. And abstract algebra is from junior level math majors classes. So I did it as part of a math education major, still in my junior year. And yeah, it was really hard. Like, not right at the beginning. It was pretty easy right at the beginning because it was like, oh, you got to define what the inverse means. You got to define what the you got to prove. You have to prove in order to use it how property of commutation or commutative property and the associative property all work. Everybody was moving too slow. and it was disorganized. Hmm. Yeah, and then we can hope that understanding everything and being right are the same thing. In terms of mathematics, right? Yeah, yeah. Sleep is surprisingly necessary. Of course, I'm here instead of in bed, but whatever. My brother had a college dorm mate, down the hall a little ways, who ended up getting basically no sleep during the entire week, like very, very little, and then would sleep 72 hours in a row. I mean, it was like, it was insane. Not terribly healthy either, but, Ugh. Yeah, I can't. I would not be able to do it. I mean, like, 20 solid hours of streaming, yeah. That'd be rough. Especially at my age with my patience. uh, yeah, I sometimes I wake up dehydrated and it's just like I didn't even drink last night. What is going on? Feel hungover and it's like that's not possible. Hmm. Yeah, unless you really limit the amount of blue light you get, it can really mess you up. So I, uh-huh. So like all of the lights in our house, pretty much at this point, are LED. They are all warm. Yep, the phone brightnesses go down at night, and um, we put on the like night mode or whatever. So at 9 o'clock when I start my streams, like almost exactly at the same time, or maybe within a 2 minute time period, everything on my entire computer turns sort of orangey. Kind of messed me up the first few times. I'm like, what is going on? But yeah, to discourage your body from all of the technological adaptations we're making, then yeah, it is better to just sort of disconnect and then make sure you actually, uh, yeah, make sure you just get off when you're supposed to get off. And I mean, it sort of depends because some people are fairly well adapted to be able to just stay up for however long, but if they're forcing themselves to do it, it's not very healthy. If it's something that your body's just naturally doing without external influence, like you could be reading a book rather than, um, hmm. So like if you could be reading a book and staying up all night and just sleeping more during a different day, then that's fine. Your body's probably used to it. You can do it. But if you're like, "Oh, I've got to stay up," and like crashing and falling asleep and all sorts of stuff like that, which I have totally done earlier, but not today, then yeah, that's not so great. And if it's the technology that's keeping you up, that's not so great. Now, keeping in mind, of course, that the only way that our species will actually evolve is if we uh, end up having people who have more children who end up doing something in particular more often. So if the people who are more adapted to technology reproduce more on average, that's the only way that genetically we're going to get that group of people to start expanding. And it's going to take hundreds or thousands of years for it to happen. But I was thinking that the dot product here was going to work, but no, not really. No, yeah, that was dot product. It's trying to like show you when you multiply vectors, how they all combine. Oops. And yeah, what are the what is the cross product? Nope, that one. Directed area product. So cross product of the right-hand coordinate system. Yep. Oh man. That's gonna hurt my head. All right. Okay, yeah. So the cross product A cross B is going to be the vector that is perpendicular to both A and B. So that's when you get your right-hand rule from A to B, that's the direction that you're going to go. So if you're talking about it as a flat plane, A to B, it wraps, and then cross product is going to be the normal vector to both of them. And again, if it's an affine coordinate system rather than a orthogonal coordinate system, then it ends up being the third dimension, whatever direction that's actually going to be in, which again may not be entirely perpendicular. Yeah. All right. Yeah, I'm gonna send everybody. Hope you have a good week, Matthew. See you on Friday for games, or otherwise, perhaps next week for math. Hope everybody else has a good week. And again, feel free to drop in whenever. I will, generally speaking, be here on Wednesdays and Fridays. Alright, Adriosa, looks like she's doing Resident Evil Village at the moment. She will be doing Mass Effect, so I think she usually does like a two game stream. Anyway, she's very fun. Should stick around. Alright, good luck, see you all later. This is Obi-Wan Pez signing off for N Simplex Pachinko. Have a good night.